The next level of problem takes us up to what to do if there's already an ion in solution, because that will not change the Ksp, but it will change the equilibrium concentrations. So when we look at this one, barium sulfate is going to produce barium ions in a small amount, but barium chloride is going to produce lots of barium ions. Matter of fact, it's going to produce one barium ion for every one barium chloride, so there's going to be a concentration of 0.100 molar barium ions before the barium sulfate has a chance to split up and reach equilibrium. So what's going to happen is best seen through the use of an ice table. It's important to tell you that no matter what, you can always approach it this way. Even if it's describing you've got a system at equilibrium and then you add the barium chloride, you can still back up and say, I can approach it this way, which is to say that your initial concentration of barium ions is determined by what is already in solution. And because we're talking about before you put the barium sulfate in, there is 0 sulfate ions. Now I include this in the table, the solid, even though it is not going to show up in the expression, just because I'm interested in making sure I haven't made some silly mistake about how many ions I get and what the ratio is for the barium and the sulfate. You can see that barium sulfate is a 1-to-1, so they're both going to be plus X. So if you picture this, I've got a solution of barium ions, 0.1 molar. I add some solid barium sulfate, and some of it splits up, plus X plus X. I don't know what that is yet. So at equilibrium, I would have 0.1 plus X and X as my molar concentrations. So the expression I'm going to evaluate is a 1-to-1 relationship. I know the Ksp, I got that from my table at the front of the package, or I would look it up in the back of a book or something. And here it comes again. This term right there, that 0.1 plus x, well, it would be annoying to have to do a quadratic. So I can just eliminate it. I actually just have to solve this equation. Ksp equals 0.1 times x, because that plus x is insignificant. It is so tiny compared to the 0.1 that we can just ignore it. When I evaluate it, I find out that the concentration of barium sulfate that dissolves, the solubility of it, which would be the same as the concentration of the sulfate, which is X, that's what I'm finding up here, is 1.1 times 10 to the minus 9. So that's my answer. The question was, what's the concentration of sulfate, or no, excuse me, what's the solubility of barium sulfate if you already have 0.1 molar barium ions, and that is 1.1 times 10 to the minus 9 moles per liter will dissolve. And if you check, if I were to add this number to 0.1, I would end up with 0.1000000000011, and when I rounded it, it would turn exactly into 0.100.